Okay, so hi everyone. I'm Regev Cohen from Verily Research. And in this talk, I will take you all the way from colonoscopy to inverse problem. The talk consists of two parts. In the first part, I will provide you a small glimpse of what my amazing teammates do at Verily Israel in collaboration with Google iDream. This will lead me to the second part, where I will try to make you rethink the way that you design some of your networks. Our work at Verily covers a wide range of medical applications. The first is colonoscopy and our polyp detector, which allows to identify and prevent cancer. Our detector displays much fewer false positives and can find even the most elusive polyps, as the one that you probably missed on the right. Moreover, we saw in clinical trials that 35% of polyps that our system detects were missed by the physicians. This result emphasizes the clinical impact of our detector. Yet, detection is not enough, since we cannot detect polyps where we don't look. Therefore, we develop an AI for coverage estimation. Here, we use our videos to construct a point cloud of the colon, which in turn used as an input to a deep network. Then, our network reconstructs the general structure of the colon, and we use it together with our point cloud to estimate the coverage of the colon. This answers two important questions. First, how much of the colon did we miss during the colonoscopy scan? And second, where exactly did we miss it? From colonoscopy, we move to microscopy. Here we use NI together with Verily high-perspective microscope to perform virtual staining. We replace the standard chemical process with a virtual process that highlights important biological markers. This allows us to extract much more information from the same biopsy without affecting the original tissue. However, most of the time, we do not have ground truth images. Hence, we develop an uncertainty estimation technique, allowing our model to simply say, hey, I don't know, or I'm not sure. We distinguish between two types of uncertainty. The first is model uncertainty, which tries to answer whether do we need more data or it is sufficient. The second is data uncertainty that relates to the variability within our data. Next, I move to surgery, where we develop tools for surgical procedure, such as our tool segmentation shown on the left. This tool allows to turn the dark image in the middle into the bright image on the right, where the doctors can easily see the different organs and tissues. So now that we can see, we would like to know that we see what we think we see. Here our automatic critical view of safety comes in. It identifies important organs, features, and crucial blood vessels. This ensures that we remain within safety protocols and provide the doctors the green light to proceed and remove the necessary organs. So, as you can see, we cover a wide range of medical applications with vast clinical impact. However, all of this development requires large amounts of data. The challenge is that medical data is often limited. So what do we have? We have a profound understanding of our medical setups and strong signal models. This leads me to the second part of the talk, where we combine deep learning with deep models to solve inverse problems. In general, inverse problems refer to the task where we are given a corrupted image, and we would like to recover the true clean image on the left. Given some model of the degradation process, which may be linear or nonlinear, we can form our inverse task by solving an optimization problem. However, typically we need to add some regularization that incorporates prior knowledge on the true image. A popular trend of recent years is using deep networks, of course, as regularization that can be either explicitly or implicitly. Here, we train a single network on a specific dataset and later on exploit it for solving different problems with different datasets. A variety of networks can be used, such as GANs, autoencoder, diffusion models, and many, many more. Here, I would like to focus on a specific approach, where we use denoiser as our priors. The first example is the plug-and-play framework, which exploits state-of-the-art denoisers within standard optimization solvers, such as gradient descent. The second is the seminal work of regularization-by-denoising, RED, that utilizes the denoiser to build an explicit regularization term. Both RED and PnP achieve state-of-the-art performance in a variety of different tasks, especially when deep networks are used. However, their stability requires careful tuning and cannot be completely guaranteed. This is crucial in medical application, since we cannot allow for unexpected behavior or phenomena such as mode collapse. Most of recent works prove the stability of RED and PnP techniques based on the assumption that the denoiser is either a map or MMSE estimator. Unfortunately, state-of-the-art denoisers are neither map or MMSE estimator. Why, you ask? Well, we show that in both cases, the denoiser should be gradient of some function. So a follow-up question is whether standard denoiser satisfies this condition. The standard approach aims to train an end-to-end network which approximates the gradient of some function or some distribution, as done in score matching, for example. However, typically the left side is an asymmetric function, while the right side is symmetric since it's a gradient function. So equality cannot be achieved. To solve this, we introduce potential-driven denoisers, which build as gradient of deep networks. There are three approaches to design such networks. The first is directly design a network that is a gradient of possibly implicit potential. However, currently there is no feasible way to do that. Another option is to take your favorite network and build our potential by composition. For example, by taking the squared norm of the network. Lastly, the most general approach is to design a scalar-valued network and use its gradient as our denoiser. In this work, we focus on this approach. To that end, we design a network G that acts as our potential function. Then, we define our denoiser as the gradient of this network. Now, if you see the equation, you can see that both functions of both sides are symmetric, and we have much better chances to obtain an equality. This leads to our denoiser, gradient CNN, whose residual is the gradient of a potential network. Our network follows a typical structure of a feed-forward network with skip connection, but with two exceptions. First, the output of the network must be a scalar, of course. Second, we use a smooth activation function, such as LU. Then we train our denoiser in a standard supervised fashion. Thus, we create three types of denoisers. The first is the one that I just described. For the second, we use in addition non-negative weights with convex activation, which create convex potential networks. Lastly, we consider a third network, which is the difference of two convex potential. This network acts as a compromise between the first and the second approach, or in other words, a compromise between expressivity and convexity. Given our trained potential, we can formulate our recovery problem. The benefits are that we have an explicit and smooth objective. Moreover, when we use convex potential, we get a nice convex formulation. In addition, we have a simple expression for the gradient which uses our denoiser. So we have the gradient, so the simplest thing that we can do is gradient descent. However, we still need to set the step size properly. It can be shown that the step size directly relates to the Lifshitz constant of the denoiser, which is typically unknown. Previous works aimed to control this constant by applying methods such as spectral normalization, RED and PnP, and more. We, however, enjoy the benefit of having an explicit and smoothed objective. This allows us to easily set up step size to ensure that every step we do is at the same direction. Thus, we can perform gradient descent using backtracking step size, and we are guaranteed to converge to a stable point. This is our algorithm, and you can see how simple it is. Although its simplicity, it is extremely effective, since it combines signal models and powerful deep networks. We test our algorithm for various tasks, such as Gaussian deep layering and super resolution. Here you can see some of our convergent analysis, showing that our method nicely converge, while PnP, the blue line, diverged at a certain point, leading to a seriously degraded results. Here are additional visual results demonstrated that our methods are not only stable, but leads to better recovery with improved PSNR. Finally, we use standard benchmark dataset to evaluate our recovery algorithm and denoisers. We achieve performance that is on par with state-of-the-art techniques, even when we use convex potential, which leads to global convergence. This proves that we can obtain state-of-the-art performance while ensuring stability, which is so crucial in medical application. To conclude, the main takeaway is the notion of gradient-driven networks, and I hope it will make you rethink when you design your networks in the future. On behalf of all of our team at Verily Israel, I would like to thank you for listening.
Thank you very much, Regev. And here's Debbie. And
hey, sorry about
take
that.
It from here.
So, Regev, let me ask you a couple of questions from the audience. So you mentioned some end-to-end networks, some standard end-to-end approaches. Could you explain what are the benefits of your iterative solutions over these standard end-to-end networks?
So there are two main benefits. One of them is the fact that using our iterative process, we can actually train a single network, a single denoisers, and then apply it to a variety of tasks. So using, for example, denoisers, we can then do super resolution or do deblurring. And especially in medical setups, we have we don't know what's gonna happen in the future. So we might encounter some problems, some new problem that we don't have data for. So we want a general approach to train or to use data once and then apply it many times in many different scenarios. So this is one of the strongest benefits of this iterative process. The second is that using our gradient network within this iterative process, we can guarantee that our solution is stable. This means, so it's not only a theoretical question, but also a practical one, especially in medical imaging, because most of this iterative process needs careful tuning that changes within different setup, different data set, different scenarios, and so on. So again, we want something that is general and requires much less tuning to ensure stability, that we will not get something that is very crazy, that is very off. As we often see in deep learning in end-to-end networks, that sometimes we have this phenomena of mode collapse, that the model works well, but on certain example, it just output nonsense and things that we do not want to see, especially in medical applications.
Thank you. It definitely makes sense. Another question: value activations.
Can you ask again? I didn't hear it.
The value activation?
The what?
Regev, can you hear me?
Yeah, now I can hear you. You were cut off for a second, sorry.
Sorry about that. So the question is, why did you use LU activation? Activation?
It's a great question. So one of the things to ensure that we even converge, we want that our network, our potential network, to be smooth. This is a relatively sufficient condition, but also allows the network to be expressive enough to ensure convergence. So once we have like a smooth activation, the entire network represent a smooth function. So when we plug it into our optimization problem, we get like a smooth formulation that we can easily solve, and we can guarantee convergence and many, many more properties.
Great. Here's another question. Can this notion of gradient-driven networks, can it be extended beyond denoising?
Yeah, of course. So denoising is just like the simplest example. If you saw, I mentioned during the talk methods such as diffusion models and score matching and even GANs. In all of them, actually, we can show that we want to approximate some gradient of some probability. However, most of the work just like take an end-to-end network and trying to approximate with it the gradient. But since it doesn't have the necessary structure, we are doomed in some sense. So here we are building our network to be a gradient. So it's a much better approximation. So we can take it and do score matching with it with diffusion models. And it's actually our next step that we are currently working on.
Here's another question. So it's actually multiple questions.
Yeah.
What about the loss functions? Are the networks supervised or unsupervised? And have you done some domain adaptation?
So currently, so this was the first work. So we just use supervised training by taking images and adding like Gaussian noise, which is actually something that we can do it with any data, and we can do it synthetically. It's okay. But we do have like additional work that use unsupervised fashion. So we can train denoiser in an unsupervised manner, and we can consider even like more sophisticated losses. So we use a standard MSC loss, but now once we have our gradient network, we can think about perceptual losses and so on, or losses related to GANs and diffusion models and so on. And as I said, it's something that we are currently working on.
And maybe one last question in the next minute or so that we have. Could you give some insight about other topics in Verily? So somebody here asked us, does Verily Israel work on other topics or research fields other than the one you presented in the talk?
Yeah. So we are working on many different things. This was only a glimpse. For example, I can say that we are also working on drug design and graph neural networks in this context. We have an amazing intern, Dayal, that is doing a fantastic work on drug design. And there are more examples that I can elaborate on for anyone that want to speak with me.